Hello, everyone. Welcome to our webinar today. Um, the webinar topic for today is energy storage and cybersecurity. This webinar is being presented by the Clean Energy States Alliance, and it is a presentation of the Energy Storage Technology Advancement Partnership. And we have an excellent panel of guest speakers with us today, but before we get to them, I'd like to go over a couple webinar logistics. We are now using Zoom webinars. This is a new platform for us, so if you have any feedback for us, we encourage you to provide it in the post-webinar survey or via email. All attendees are in listen-only mode, so your webcam and microphone are disabled, as is the chat function. If you'd like to submit questions and comments, you can do so via the Q&A panel. We will be saving 15 minutes at the end of the presentation to address Q&A questions, so feel free to submit your questions throughout the webinar, but they will be addressed at the end. Automated captions are available, and speakers' bios will be made available in the chat. Finally, this webinar is being recorded. We will email you a webinar recording within 48 hours, and it will also be posted on CESA's website at cesa.org/webinars. And with that, I'd like to pass it over to our host for today, my colleague Todd Olinsky-Paul.
Thanks, Zareen, and welcome again, everybody, to another in our long-running ESTAP series of webinars. We are in the 13th year of these energy storage webinars, and in case you are relatively new to them, if you would like to go back and look at the previous ones, they're all archived at the CESA website. So I'll do a brief intro, and then we'll get right into the meat of today's presentation. In case you are not familiar with CESA, the Clean Energy States Alliance is a national nonprofit, essentially a coalition of state energy agencies and organizations. We are celebrating 20 years in the field, and among other things, we work with states to advance energy storage. If you could advance the slide, please. I think we have here, yeah, we do. We have a slide that shows our state membership, which is quite large. The next slide, please. So a bit about the ESTAP program, the Energy Storage Technology Advancement Partnership. The core goals of the program are to facilitate public-private partnerships to advance energy storage demonstration projects, and also to support state energy storage efforts with technical, policy, and program assistance. And thirdly, to disseminate information to stakeholders through webinars such as this one. We also produce reports, case studies, conference presentations, and so forth. And all of that is also archived on our website. Next slide, please. So we are going to be talking today about energy storage and cybersecurity, a topic that I've been quite curious about myself, and it's often referenced but seldom explained. So hopefully we will have a better understanding of it after this webinar. We are joined today by Ram Ganti from the Electric Power Research Institute, EPRI, and Howard Gugel from North America Electric Reliability Corporation, NERC. In addition, we have a couple of guests who are not going to be presenting, but will be joining us for the question and discussion session following the presentations. And those are Dr. Imre Juk and Xavier Francia. And well, I'll let them introduce themselves when we get to the discussion portion of the event. But we do want to thank Dr. Juk for his long-standing support and efforts in the support of energy storage and of the ESTAP program. Next slide, please. You could advance the slide. If that's the last one, then we can go right up. Right. So let's go right into Ram's presentation, please. And I'll turn off my camera and see you afterwards. And by the way, if you do have questions, please enter them as you think of them into the question panel, and we will be sorting through those as the presentations are being given.
Sounds good. Good morning, everybody. Thanks for joining this webinar, and thanks to the CESA team for providing this opportunity. I'm Ram Ganti, a technical leader at Electric Power Research Institute. My research areas are primarily focused on DER cybersecurity, and I'm joined by my colleague Xavier Francia, who's a principal technical leader leading the efforts in securing DERs and their interconnection with the grid. So in the next couple of minutes, I would like to provide a brief overview and talk about how the cybersecurity is going over for utility scale energy storage systems that are typically connected to distribution or transmission grid. We'll talk through challenges, learnings, and also look at how the architecture looks like. And we work with a lot of utilities, so these are some of the insights that we got over the years doing a lot of projects with them. So I hope you find this informational. So battery storage, they come in various sizes and capacities, and based on what the need is, kind of services they provide, but fundamentally their functionality remains pretty same. They provide energy in some sorts, and as you can see, there are smaller batteries that provide power to our mobile devices or vehicles, and then you have larger scale energy storage systems which are possibly connected to grid or provide power services to a residential or buildings. I'm going to talk more from a cyber perspective, how the impact is based on the size and what changes. So greater the size, higher the impact on grid, it has more momentum, more power, so it can cause larger disturbances on grid if systems like these are compromised, especially in larger numbers, right? And the only thing that changes is the complexity in the electronics, how they discharge, charge, and also the protection equipment and monitoring requirements. So a small battery that's in your phone could just operate at a very low complexity, but something that's connected to the grid might need to be synchronized with the grid in terms of phase and how it is outputting power. It just can't directly put power onto the distribution grid. And discussing the architecture of a generic storage system, if you look at from a very high level, what are the blocks inside energy storage system? You have EMS, which is a software suite, which consists of a lot of interfaces for HMI, and it has access to historian servers and data storage, and also ability to configure the networks that control the devices which are underneath. And then you have the power conditioning system, which is basically responsible for taking all the DC power and then make sure there is power quality, the waves are smooth, and also includes circuit breakers, islanding, anti-islanding control, and also some protection equipment like circuit breakers, relays, or fuses that enable secure operation of the energy storage system. And the last layer we have is the battery management system itself. These are usually in the containers itself, or you could have a centralized battery management system. But overall, the purpose of a BMS is basically to monitor all the battery packs, the lithium ion or whatever technology it's using, and monitor the state of charge, cycle count, and how the cell health is going. And it also ensures that during charge and discharge, these processes happen evenly and don't wear out particular cells. And it also would have a communication interface if the OEM decides to communicate or pull any kind of telemetry from these systems. So this is an overall very high level architecture of energy storage system. This is how it looks like if you see a large battery pack, if you're driving by a PV array or any energy storage system. So what are some of the challenges that our utilities or in general we have in securing the energy storage system, cybersecurity standpoint? So very quick, there are a lot of challenges, but like coming from a priority, cost, and resource and impact perspective, I think these are the 6 or 7 that come to my mind, which is one is securing integration of third parties and vendor remote access to the ESS. This has been a big challenge, continues to be a big challenge with utilities where these energy storage systems are not monoliths. They are usually integrations from various vendors, OEMs. So there are a lot of stakeholders involved in the operation of a large-scale energy storage system. So there are usually third parties or OEMs which would love to connect to these systems during their span of operation, whether it could be for analytics or monitoring or for warranty purposes, or even in some cases, they could exercise some kind of control by performing right operations. So that is one challenge. How do you securely integrate that? There are a lot of solutions for that, but that continues to be a challenge. And next one is developing and testing security controls for systems that may not suppose complex processing or latency sensitive. This is a common issue in the OT world where you cannot just perform security testing or any kind of scanning or evaluation on a live system, because most of these devices might not have enough CPU headroom or network bandwidth to respond to scanning requests. So it could cause any kind of malfunction, or the devices might simply trip, and it's not safe to do so. So developing a test plan that is secure enough to perform in an isolated environment and then ensure that it works as intended in production is a significant challenge. And then we have a lot of gaps in interconnection requirements between utility and vendor offerings. This gap is getting smaller as there is more information exchange between the interconnection requirements, the NERC sub-regulations, and also what the product exactly can support. For example, if a BMS or EMS needs to ensure all communications have to be encrypted, it's not just the requirement, but the hardware also needs to support that kind of requirement, also at the capacity of bandwidth that's happening at the site itself. And then securing data across ESS operations. So on-site and cloud, I mentioned that specifically because unlike the good old electronics or electricals, most of the systems that are today are do-it-all. They have a lot of interfaces. They can connect to Wi-Fi, Bluetooth, and they might also have some proximity connection technologies like Zigbee and stuff. But most of the data telemetry is likely to go into some sort of cloud, whether it's vendor managed or the utility managed cloud. So securing that data takes a lot of effort and resources to get in and make sure all the telemetry is secure. And in case of a security compromise, how much information can an attacker or an adversary get from those? And then developing risk prevention and mitigation strategies for different ESS architectures. Even though all utility scale energy storage systems are similar in functionality, they could be very different in characteristics, like where it is connected to, what kind of services it provides, and things like that. So that determines the overall impact it would have on the distribution grid, and hence overall determination of risk by multiplying impact and likelihood. And so developing a tailored risk mitigation strategy is very crucial for utilities. And lastly, we have enabling physical security with strict electronic perimeters. We have seen a lot of kinetic attacks happening on substations and critical infrastructure. So it is important, based on how much power does the energy storage system have, to enforce a physical security perimeter along with electronic security perimeter, by which I mean if a device has some kind of radio capability, wireless or Bluetooth, you have to ensure those signals are not being accessible far enough that an adversary is comfortable to perform any kind of reconnaissance. We'll quickly go over energy storage architectures to security architectures more to understand where are the pain points from a cybersecurity standpoint. There are a lot of architectures when it comes to storage system. It can be configured in multiple ways, but from an access and network standpoint, we have divided into just two of those, which is vendor read-only and vendor monitor and control. So I'll discuss about the read-only. Read-only part is straightforward, where you as a utility have a very large energy storage system, but you have certain components that are vendor provided. It could be coming from company A, B, C, but they want to access the telemetry, battery health, your schedules and firmware information, configuration information, whether it's for backup or it's for analytics, or it is just to maintain warranty through the period, 5 years, 10 years, whatever it is. So in such cases, the risk is very minimal, but you have to ensure vendor access into the system. How do you do that? So there are two options. One is either the vendor goes through the regular authentication mechanism through the utility corporate network, where the utility will decide how they authenticate and may have more granular control on the sessions and stuff. And the option B is the vendor would say, hey, I could just install a cellular modem on site on the specific system or within the best site, and say that we'll directly have access to the device and pull the event logs or necessary information. So in that case, a utility might have an on-site firewall, which could help provide visibility into what the vendor is doing and have more granular control on what URLs are accessed, what ports are enabled or not. So some of the cybersecurity concerns here in this particular architecture would be data security for vendors. You have to ensure how they're transporting this data and where do they store, and also the lateral access part of this. If the vendor ends up putting a cellular modem on site, what kind of access does he have to rest of the systems? Can they scan? Can they know what hosts are on the network? Things like that. And also deep packet inspection at low level would be really helpful, just in case if the most vulnerable device is compromised, you don't want that malware or any kind of security concerns to be flowing laterally to rest of the devices. And this architecture is just opposite of that, everything plus vendor monitor and control. This is where the vendor is still accessing through one of the ways that I mentioned, but they're also able to exercise control, which is make some write changes onto the devices. They can physically impact the system. They can either charge it, discharge it, or modify schedules or update firmware and things like that. So in this case, a lot more scrutiny is required as to what the vendor is doing. So first steps would be like evaluate the vendor's control processes. What are the thresholds, override capabilities? If the vendor is compromised and they send out discharge schedules that are going to stress the system out, then do you have any override capabilities as a utility? Is that in your agreement, right? So there are things like that. And also evaluate vendor security practices on enterprise network. Just get a poster of how they're managing their data compliance and what type of cloud vendor they use and things like that. And then also data security for on-site and off-site historian. This is also part of the vendor security practices. Lastly, there are a few learnings we had from a lot of projects, which I'll try to summarize here. But before that, I'd just like to highlight on the diagram on the right, which says architecture variables. So impact can be determined based on various variables. So some of the top four categories that we came up was point of interconnection. Where is it connected? Transmission, distribution, generation, or is it just a residential scale DER that is aggregating and providing power, And then we have the ownership aspect, because it determines whether if you can walk to the system and troubleshoot it should something go wrong. Is it utility owned or third party owned, or is it residential? And then access level. What kind of access do you have? Is it, like I mentioned, is it read only, read and write, or do you have a simple remote mechanism to get into the system and perform any operations that you want? And then last thing is grid services, right? The criticality of the system depends on this, because something that's connected to a military base or a microgrid is way more critical than something that's just providing grid functions, market services. Something like a black start is even more critical, right? In case of a large outage, you want a system that can boot up and set the phase so that rest of the systems can follow. Coming to the learnings, what we have observed, most of the large-scale energy storage systems have remote monitoring and data acquisition. Basically, data goes in and out to the cloud, so it needs to have some sort of connectivity unless it's under DoD or some other restricted areas. And firmware method updates, we have seen a lot of those, but preferably if it is coming from the vendor's website and it is assigned firmware and happens at a particular schedule where you can also test the firmware on a separate environment to ensure function testing and unit testing. And then you can deploy the OTA wireless is the preferred method. And then you have remote, where if the system itself can be virtually remote in through tunneling and VPN, all those security measures, that would be preferred. And the last one would be in person, where you would need a lot more vetting as to what devices are being brought in, and you need to perform security testing for those before they can connect to your OT system. This is for very large scale energy storage systems where any potential compromise can cause loss of service and resources to the utilities. And then, like I mentioned, the third one is crucial to have east-west monitoring, which is you just don't do security monitoring at the top level for the systems, but you also monitor traffic that's going between the lower level serial devices, right? That is important, because a compromise there, for example, a spoofed temperature sensor could essentially make the EMS blind on how hot the batteries are getting, which could lead to thermal runaway. That's a very basic example, but having east-west communications allows us to see if at the process level, things are not compromised. And establish electronic security zones, I think I've spoken on that. And whitelisting critical assets after determining baseline traffic. This is very network security 101, where once your system is commissioned, you baseline the traffic, you capture all the traffic that's happening between various systems and identify this is the baseline, this is how the system operates under normal conditions. And then you allow your assets to communicate with other assets based on whatever you have observed in the baseline. So that would be whitelisting. So any other communications that are outside of this norm might be allowed based on exception and prior knowledge that this communication is going to happen, right? And then the last one is remote access. So some of the practices that utilities follow are they'll stage whatever vendor requested data is in a separate secure environment. It's more like a proxy. Instead of vendor remoting into the whole utilities network, here is your separate secure environment, and we'll host the data here, and you can pick it from here. So these are some of the learnings, and with that, I'll stop here and hope that was useful, and look forward to any questions for myself, Xavier, and Howard on the Q&A panel.
Great.
Thank you.
Thank you very much. We're going to get to the questions after the second presentation. So we're going to go ahead and go over to Howard and get his slides up.
Good afternoon, everyone. My name is Howard Gugel. I'm the Senior Vice President of Regulatory Oversight at NERC. Presentation today, basically, I'll give you an overview of who NERC is and kind of what our responsibilities are. I'll lead then into a little bit of the observations that we've made over the last couple of years about what's happening on the system. Talk a little bit about the importance of battery storage and why our clean future really is tied to some sort of a model that has battery storage associated with that, or energy storage associated. And then finally, some of the cybersecurity concerns that we've seen, or things that we think attention needs to be paid to for that. So who is NERC? NERC is the North American Electric Reliability Corporation. We are, at least in the U.S., the ERO, or the Electricity Reliability Organization. That ability was granted through Section 215 of the Federal Power Act. So we have a statutory ability to assure the reliability, resilience, and security of the North American bulk power system. That has many responsibilities that go with it. We develop and enforce mandatory and enforceable reliability standards. Those are all on our website. Those include everything from operating, planning, and maintaining the system to cybersecurity standards. And again, these are mandatory and enforceable standards to folks that operate, own and operate the bulk power system. We also do seasonal and long-term reliability assessments to see how the transmission system or the bulk electric system is performing, any areas of concern that we've got, and that information is used to help inform both regulators and Congress to understand where some of the issues are and where attention might need to be paid to that. We also actively monitor the bulk power system through system awareness. So we're able to pull in strategic points across North America on all 4 interconnections. We can see how flows are occurring there. And if anything were to occur on the system, we can provide real-time updates to any applicable partners that need to have that information. And then finally, we educate, train, and certify certain industry personnel that actually do the operation of the system. So you can see we do things that deal with critical infrastructure interdependencies, security risks, extreme events, and grid transformation. We see really that there's 4 pillars for the energy transition. It deals with, first of all, the fact that we need low or no carbon energy resources, and that we need to have a sufficient amount of those. And I'll talk a little bit later on the slides as to what that trade-off will be. But looking at, how much energy do we need to be able to go through this energy transition? We also know that we're heavily dependent upon transmission, and that a lot of times where clean energy is available is not necessarily where the load's at. So you've got to have a way to transport that energy to the load pockets, and transmission certainly is an important part of that to get that energy transmitted across North America. We also need the ability to balance resources. The electric system is very unique as you compare that to other systems around the world. The electric system is an instantaneous, so energy is consumed as it's generated. Anything that's not stored, that is. And so we need the ability to balance that. You need to make sure that load and generation are always in a balance there. And then finally, as we begin to develop more and more new resources on the system, there's a concern about supply chain, whether or not there's adequate pieces of equipment to be able to put on the system, and also whether or not those pieces of equipment are secure all the way from manufacturing to installation. So what are some of the concerns that we've seen on the North American grid, and why is energy storage so important for that going forward? First one, and you see the first graph here on top. If you look at the Midwest, we have a significant amount of wind that is installed in the Midwest. In fact, 60 gigawatts of wind. There was a situation that occurred back in 2023, so couple of summers, year and a half ago, in early June, where of that 60 gigawatts of installed capacity, only about 330 megawatts were available. So a significant amount of reduction there. And it was because there was a wind drought. There just wasn't wind available. And so, operating the system, the operators had to figure out, how do we make up those resources? Again, if we had adequate amounts of storage on the system, it wouldn't be quite as much of a concern. At that time, there was a little bit of scrambling to see how we get the capacity and energy available to be able to meet the load concerns. And then another situation is sometimes you've got areas where you've got energy available, but you can't really get it out because there's transmission constraints or system constraints to getting that energy out. And one solution that I just happened to show here during PJM scenario in Elliott, there was transmission constraints to where there was energy that was available but couldn't be transmitted. One solution for that would be on the side of the constraint. If you had energy storage available, you could free up some capacity there and be able to offload some transmission. So good solutions that we could see there. And then the next step is, okay, so how do we go through this energy transition? What's necessary for that? And so just a thought exercise here to kind of help folks kind of think through it. If I'm going to retire 100 megawatts of baseload generation, be it coal or whatever, and replace that with good, clean resources, what do I do? My example here is, let's say I do it with a combination of solar and batteries, because of course, the sun doesn't shine at 2 o'clock in the morning. And so I've got to have the ability to cover that load 24 hours a day. And batteries or any type of energy storage device aren't really generators. They're really time-shifting devices. I can take energy when it is plentiful and available. I can store it and then use it at times when other energy is not available. So make an assumption here. Let's assume that for 365 days a year that I've got on average about 8 hours of sunlight that would be available. And I'm also assuming in this no losses and conversion. I'm an engineer, so kind of get tied up into those things. But if you take those two assumptions into account, we would need to replace 2,400 megawatt hours of energy with some combination of solar and batteries. So I need 100 megawatts to do an exact replacement while the sun is shining. So I can do 100 megawatts during those 8 hours. That would replace at least the time when the sun's shining for that resource that's being retired. But I also need to cover the other 16 hours that I'm not getting output from that generator. So I need to install some sort of a combination of solar and batteries for that amount. So I'd need an additional 200 megawatts of solar. to charge the batteries. And then if you assume, which most commonly right now, we use lithium-ion batteries for for high transmission voltage storage. Those essentially have a maximum draw of about 4 hours. So I'd need 400 megawatts of storage for a 4-hour discharge on that. So to replace 100 megawatts of baseload generation with an equivalent amount of energy, I'd need to put in 300 megawatts of solar and 400 megawatts of batteries. Essential for our energy transition, but also you're seeing now some new technology that, as you heard on the previous presentation, really has a lot of interconnected ability to tie in for that. So what are the cybersecurity concerns that we would have? And this really relates to both the inverter-based resources, so both the generators that would be tied in for the clean energy, and then also any type of energy storage that would go in place. As you heard before, one concern is remote connectivity. The ability to for a vendor or for some person to dial in and access that and to make changes on the system. You'd want to be sure you're protected for that. And then common mode issues. I'm going to put that in air quotes here. The fact that I have many of those units, maybe by the same manufacturer or using the same control system, that they could all be accessed at the same time. I'll give you a good example of that. This isn't necessarily directly related to energy storage, but it is something that would kind of represent what could happen for a remote dialing or remote access capability. We had an issue that occurred on the system back several years ago, where we had several inverter-based resources, combination of solar and wind, that for an event that occurred on the system, a bunch of those came offline, thousands of megawatts. We determined that in doing our events analysis on that it appeared that it was a control system issue with those generators. And so we got with the manufacturers and said, we really think we need to get this updated. And the manufacturers, for the most part, were, yeah, that's great. We can do that easily. We'll take care of it. And in fact, a couple of months later, we made another touch point with the manufacturers, got them to provide some survey responses, and about half of them had already been updated. The one caveat to that was, in all of those instances, nobody had actually set foot on the site. They were all done remotely. And so it kind of raised a kind of a wow factor in two perspectives there. One, wow, isn't it great that we're able to respond quickly, fix a problem, and really adjust to the way things could work better on the system in a more reliable manner. But then the other wow is, wow, if this were to fall into the wrong hands, or if a wrong setting was placed in there, this could have really been a bad situation. And that kind of brings me to another thought here. Usually when we think about cybersecurity, we're concerned about bad actors or somebody attempting to do something bad on the system. I would say that cybersecurity also involves not just bad actors, but when an accidental wrong thing can occur. So think about, maybe everything had the good intention here, but if somebody had accidentally put in the wrong control system, they could have updated all these systems in the wrong way with the good intentions there. So cybersecurity not only deals with protection from bad situations, but also human error. And then again, there's concerns about supply chain. We do know that, as you do look from source to installation, that there's a lot of hands that can touch that. And the ability to have some sort of a compromise that could occur there is a concern too. And then a lot of the resources, at least historically, have been at each location in a small amount. We have traditionally at NERC registered folks that are greater than 100 kV and that have an installed capacity of greater than 75 megawatts at a single location. As we begin to see more and more of these resources dispersed, we're seeing it to begin to affect the system at lower voltages and at smaller local amounts, but spread over a larger surface area. So we made a change in our registration a couple of years ago, and in fact, we're in the process of identifying and registering new folks that meet a lower criteria for that. So any generation, any inverter-based resource that is installed that is at a location greater than 20 megawatts and is connected at a voltage greater than 60 kV would be registered and subject to some new NERC standards going forward. And in order to facilitate that, we have initiated some communication efforts. So if you go to our website, you can see a lot of information that we have about inverter-based resources, all of the events that we've seen there, some of the cyber security concerns that we've had about, about supply chain, and then also low impact systems. We provide some quick reference guides, some frequently asked questions and responses to that, and then various educational materials, in addition to webinars that we've done over the last year or two to continue to do outreach and information on that. And with that, I will turn it back over to you, Todd.
Great. Thank you so much. That was fantastic. I'm going to ask the speakers to turn their cameras back on, and also the folks joining us for the question and discussion portion of this webinar. And thank you for being pithy. We have a good amount of time left for questions, which isn't always the case. And we have a good number of questions. So a couple of people have asked if an actual cyber attack on a storage system has taken place, and by this I think is meant a malicious attack, not a sort of accidental occurrence. And can you give an example, if so?
If that's addressed to me, I'm not aware of an actual event that could occur or that has occurred, but certainly it's something that's in the realm of possibility that could occur. And so that's why we have concerns both for solar and wind, which are inverter-based resources, and then also batteries that are connected through inverters.
Okay. So next question, this is for Ram. Can you expand a bit more on the topic of establishing electronic security zones? Have you looked at how we can integrate potentially untrusted electronics, perhaps even tampered with electronics, to still build a trusted system?
Sure. I think some concepts of zero trust might be applicable here to evaluate if that untrusted system can be evaluated for potential functional dependencies. And that way, what are the areas where you can trust. And if there is any telemetry that can't be trusted, possibly you can have redundancy on that from another vendor. That way, you'll have a two-factor look into whatever parameter that you're looking at. Also, some guidance on the SIP 15 where you have the network monitoring, and with ESPs, I think those requirements can help you identify any anomalous behavior from this untrusted device and isolate it from the network in case of a compromise.
Okay, I think we could follow up on that a little bit because we have some questions that are related about supply chain security issues. So I think if we could broaden that question out just a little bit, what can be done given that supply chains are complex and change, subject to change, and we don't always have control over sources of components and so forth? What can be done to best ensure that the completed system is still secure without having to sort of control all of the sources of all of the components and so forth?
This has been brought a lot in the ESS cybersecurity topics, but like one straightforward answer at the very lowest level is anything that has silicon or ability to decide or make functions has to be manufactured within the United States. So it's mostly lithium, bare lithium, or battery packs without the brains that you import, and rest of it has to go through a vetting. But also concepts like SBOM, software bill of materials, or even having a scan of the silicon chips that are there on the battery controllers would help to ensure the integrity is there. And there are also a lot of electronic technologies like JTAG and other means by which you can verify the integrity of a component, whether it has been tampered and it is all the register values and everything is returning as the specification was intended. But at a very high level, yeah, if it has anything, a silicon die is there, then you better have it inspected thoroughly. Otherwise, you just get the raw battery packs.
Yeah, the other thing that I would add to that too is, we also have a supply chain standard at NERC, and we require entities to do a risk analysis. So, look to see what kind of risk that particular piece of equipment could provide to the system, and understand what it could be if it was compromised, what kind of security you need to put around it. Certainly, securing all the ports and services into that particular device to make sure that you can control any incoming and outgoing communication that occurs there. Basically, also putting into your contracts or working with your vendor to make sure that you have agreements in place so that if there's a compromise at your vendor, you're immediately notified of that and can take any actions there also. And then I think having a really good response and recovery plan locally to say, okay, if I am compromised, how do I get out of that? What do I do with my piece of equipment? Is there a way to, go back to a baseline and reinstall things that I have for my side? So it's really, it's a lot about not just making sure that how things were placed in and the good practice of having things, I think, done here in North America, but also having a plan in place. A plan for what's my risk, and then a plan for how do I recover if a bad day occurs.
Yeah, if I may add to this discussion on supply chain, I think Howard and Ram make really great points here. So Howard discuss, well, here are some of the kind of the first steps that anyone could take on securing your supply chain. There's really some of the basic cyber hygiene best practices that could be done early, whereas some of the things that Ron mentioned, some of the more like advanced things that you could do related to H-bombs, S-bombs are probably more advanced security tactics related to securing your supply chain. One thing I will add is, on kind of the notion around hardware-based bill of material, software bill of materials, and for those of you who are not familiar with those concepts, basically the idea of bill of materials is the analogy I've seen is a nutrition label that's pastes on a product to provide you the list of like ingredients, or in this case the different software libraries components involved in that system. And kind of the idea there's like, well, if we had essentially that manifest, we would be able to understand what are some of the prevalent vulnerabilities that would be associated with those technologies. So that's an ideal state. I would say this industry still has quite a long way to go, and this is definitely a big area of research that a lot of folks are interested is H-bombs and S-bombs, but really one of the difficulties around that is really the operationalization of that technology. I believe that technology is there, but there are a lot of different like legal concerns, how to actually take advantage of that information to really provide a lot of like security value there. But definitely well worth the effort of research and development to get us to that state one day. And the second thing I'll add regarding supply chain, and this kind of goes back to one of the earlier questions around cyber attacks that we've seen. A lot of the cyber attacks that we've seen, not particularly to energy storage systems, but DRs in general, we seem to be seeing a growing trend on cloud-based attacks. A lot of these DR systems are cloud connected, and both what we've seen in both in the research realm and some events are like vendors specifically not managing their cloud security, where they are now able to get into those cloud-based systems and push bad firmware, for example, to multiple devices. And I think that's sort of where the bigger supply chain concern is, being able to leverage cloud to really expand the scale of your cyber attack.
Well, thank you. That kind of leads to a question I had, which is, are the cybersecurity risks of energy storage qualitatively different from the cybersecurity risks of other energy technologies? Is there something about storage in particular, or is it pretty much the same kind of risks, and it's just that the industry is relatively new and needs to catch up on security and protocols and so forth?
So I'll start with this, and my friends can add to it. I don't know that it's necessarily unique to energy storage or battery storage. Certainly inverter, at least what we've seen, most of the newly installed inverter-based resources tend to be remote connected. So the ability for a vendor to connect to it remotely and to do any type of warranty information there makes it a little bit more unique than maybe some of the past installed generation and devices that we've had on our system, which have typically not been connected that way and typically require some sort of a man-machine interface to do any sort of updates and a thought process before that's done. So is it unique in general? No, but I think a lot of the newer resources, battery included, tend to have more of a remote connectivity issue than maybe some of the traditional stuff.
Okay. I think, Howard, question is for you. What best practices or guides exist for battery energy storage system installations that fall below NERC registration thresholds?
Oh, that's a really good question. There is nothing that would stop anyone from still using what we have in our standards for lower thresholds. I think there's also several resources that folks can get to, whether it be the electricity ISAC or other entities that have good practices that can be used there. Certainly NIST can provide some information on that too. But that's kind of where I would say I'm going to go to my fellow panelists and see what their thoughts are on that too.
Yeah, I could speak to some of the more general like cybersecurity guidance and practices. Not necessarily associated with NERC, but some of the things that have been introduced to the industry to with really the overarching goal of like kind of establishing really a cybersecurity framework for really the DR industry. A lot of like guidelines that we've been paying attention to, like the first one is 1547, specifically 1547.3, which is a cyber security guide for DR systems interoperating with the grid. And currently there are big discussions being held on like, well, with .3 being guidance, what would actually be some among that guidance, the more enforceable requirements that we want to bring into the base, 1547 standard. So some ongoing discussion and working groups, happening there. I would also cite the NERC cybersecurity baselines. That is something that has just been recently published in late last year with some implementation guidance just published a couple months ago. That's something that we're kind of taking a look at, and a lot of the issues that have been discussed here in this panel related to supply chain issues, things around like asset management. There are some set of baselines being discussed and established around under NERC. But one of the more like interesting cybersecurity standards that we're particularly facing or focusing our attention to is really the emergence of cybersecurity certifications. In the last year or so, we've had several entities like Sunspec Alliance introduce their version of cybersecurity certification. We have UL, as many of us know, UL 1741, is being leveraged by several state jurisdictions to establish some technical requirements around certification of smart inverters. UL is also looking at the same thing from the cybersecurity side via UL 2941, and looking at that to develop cybersecurity requirements for inverter-based resources there. So that's something that we're looking into as part of our research over here at EPRI. And what we're kind of saying is there is a bit of an apples to apples comparison where some certifications cover this thing, whereas another certification covers another thing. But one thing I will caution around like certifications is really kind of acknowledging that cybersecurity is an ongoing process. A lot of these certifications are this one-time thing where they look at a product category or product offering and look at its cyber capabilities. But it's a whole nother issue around like the implementation of that security and maintaining the cybersecurity over the lifetime of that device, as vendors, apply configuration updates or, touch these systems, perhaps new vulnerabilities are find over time, or disclosed. So one thing important to understand is, certifications have their specific place in the security solution, but it's certainly, not a, one solution, for everything.
Okay, thank you. Just quickly, based on what you're saying, should I be worried if I, for example, install a Powerwall in my garage and it is connected through my Wi-Fi, for example, to other controllers and things in my home or outside my home, maybe a third party is involved. Do I need to worry that some bad actor is going to set my garage on fire?
I think the bigger risk on that I see is if the whole manufacturing, if the software part of that manufacturer gets compromised and a much larger orchestrated attack takes place where all the Tesla Powerwalls are putting power back into the grid with slightly out of phase and disrupting the harmonics and things like that. But personally, I believe for most of the energy storage systems at the physical level, there's always an envelope within which a battery operates. So there are like physical barriers which simply can't be broken with a cybersecurity, just like your 15 amp fuse. It would blow at that particular threshold. So the likelihood is very low, but given how many things are controlled via software and how much of it is actual physical barrier to make an accident happen, I think that kind of evaluation on a device would give a better answer if thermal runaway is possible through a Wi-Fi connection.
Okay, thanks. We have a question from one of CESA's state members. What advice do you have for a state energy storage program? And this is from a state agency that is engaged right now in putting together an energy storage program to help meet their state's storage target. So they are engaged in designing energy storage incentives and procurement requirements and so forth. So what advice do you have for them?
Yeah, so the first thing I would say is you've taken a great first step. Some folks don't even think about, what sort of coordinated policy or what should I be putting in place for my state to be able to do this. So I think stepping back and trying to get a good handle of what is the risk, what kind of impact could this be to my state, is a first step. I think the second one is to start engaging with, with folks who are involved in this. So, looking to, again, like I mentioned earlier, the electricity ISAC or engaging with other states to see what best practices are out there, using NERC to kind of get some information on that. And then, you know, becoming informed. Attending webinars like this kind of helps you become more informed of the issues. And I think attending more of these types of forums and understanding more of the issues can help inform how you go forward with these sort of policies that you have.
To the extent that they can control it, should the state try to exclude, for example, products manufactured in particular countries, or in other words, you could, for example, develop a list of approved equipment that would qualify for an incentive or satisfy a procurement requirement, and you could exclude certain things. Is that something that should be considered?
Yeah, one thing I'll add, the whole like area around, you know, whole geographic bans of products. Long story short, I'm not too favorable of that as a security strategy. If you think about the supply chain, you know, of course, you know, you may have, you know, things, you know, manufactured overseas, but maybe it was like, you know, assembled within you know, United States. So you may have like, you know, a US, you know, based company, but in reality they're supplying, you know, a lot of different, you know, components from, you know, elsewhere around the world. So, you know, it raises a lot of questions on like, well, you know, what does a, you know, whole geographic ban, you know, look like? You know, is it just a brand, or is it, you know, also, do you also include all the internal components of the system? And you know, as you know, some of the things that, you know, Ron mentioned, a lot of, you know, vulnerabilities could, you know, happen, you know, at any point in the supply chain. I would say like the better security strategy here, you know, as you know, Howard mentioned, is really around security monitoring, incident response. You know, when a cyber attack does, you know, happen, you know, despite all your efforts to, you know, protect it at implementation, you know, there still needs to be a good, you know, incident response plan to ensure that you're minimizing the scope of the attack and, you know, minimizing its impact here.
Thank you. Now, we are talking about energy storage as a technology that may be vulnerable to cyber attacks. I just want to flip it around for a minute. Are there ways in which energy storage could contribute to increased cybersecurity? And I'm thinking here, for example, microgrids that are storage-based could be isolated and thereby more secure. I think that's something that some of the military applications are considering. So are there, I guess I should say, are there instances where energy storage might help contribute to increased cybersecurity?
Say reliability, yes. Cybersecurity, maybe not much. If it is powering a system or a building that is responsible for black start or something, in that case, we can say in some way it's helping to secure the grid to recover from a black swan event.
Yeah, I would agree. I think the distinction there is you're potentially increasing reliability by using the storage, but I'm not sure that it's necessarily improving your cybersecurity posture.
Okay. Thank you. Are there any cybersecurity assessments required by utilities during the utility transmission interconnection process? And if so, how long do they typically take, and what are the most common challenges faced by developers?
I can provide a quick overview of that, although I have limited information on that question. So the interconnection processes are long so far, from what we have heard from utilities and both the vendors as well. And what was the first part of the question, Todd?
Yeah, so the basic question is, are there any type of cybersecurity assessments or analyses required by utilities during the interconnection process? So you are a third party looking to interconnect a battery storage system or some other energy storage system onto the transmission grid. Do you have to go through some kind of cybersecurity assessment in order to be able to interconnect? And what does that look like?
So the interconnection agreement has a lot of language on enforcing what the system, what is expected of the system during its operation period. It has some cyber language on it. Some utilities which are bigger have more footprint in terms of their distribution lines. I think they have a lot more emphasis on cybersecurity, but I'm not sure if there is exclusively a template for a cybersecurity checklist that can be sent to a vendor or anyone who's integrating in.
Yeah, I would add, we're not quite aware of like any utilities, right now, kind of exercising a specific cybersecurity review process other than their, normal third-party security review that they have for like any other vendor, regardless whether they are DER or not, as part of their interconnection process. But I will say, like, considering we're looking at these distribution connected systems, really the whole like interconnection process is right now for a lot of utilities really the only enforcement process in ensuring that cybersecurity requirements are met. Now, what that looks like, I think a lot of electric utilities that we've spoken to are kind of looking into that and kind of defining that process. But I think in general, like some of the things that we've been seeing or being discussed is like, well, there may be multiple tiers of what that process look like. So if you're looking at a residential small system, uh, of course, an exhaustive review probably wouldn't be necessary or not really commensurate to that. But for a very large scale system, uh, more than a megawatt, there may be like some additional requirements. For example, a full cybersecurity review, but also like addition of like specific cybersecurity technologies that a utility wants. We've heard like, for example, the whole concept around DER gateways as being a piece of technology that are being required, as part of that interconnection in order for utilities to securely communicate and interoperate with those, larger scale systems.
Okay, thank you. Well, I wish we could continue this because it's really a fascinating conversation, but we have actually exceeded our hour, and unfortunately, we're going to have to end. Thank you so much to everybody, all of the presenters and folks who joined for discussion, and to the attendees. The slides and the recording will be made available on the CESA website if you want to review it or know somebody else who would like to take a look. And I will turn this back over now to Zareen to tell you about a few upcoming events.
Thanks again, everyone, for attending this webinar. We do have a good amount of upcoming webinars in April. If you would like to read more and register for those, you can do so at cesa.org/webinars. Like Todd said, we will be emailing you a link to the webinar recording and slides within 24 hours. Thanks again, everyone. Have a great day.